However, when the steady state approximation does apply, we do have a rate determining step. Okay, and that goes as the following. So A goes to I with rate Ki, and I goes to product at rate Kp. And when this first step is slow and when the second step is fast, or in other words, when Kp is much greater than Ki, we have the steady state approximation, and the reaction appears as if it just goes A goes to products occurring at rate Ki. And so let's set that up in the Mathematica here. So if I just jack K2 way up, okay, and I'll turn Ki way down. So you can see what we've got going on here. I is produced at a steady rate. So in other words, what we can really say is going on in the steady state approximation is the production of I with respect to time is approximately 0. So in other words, the rate is at a maximum and constant value throughout the reaction. Approximately. You know, you can see that this does have somewhat of a negative rate if you've got really good eyes, but this is approximately di by dt equal to 0. Okay, so let's keep going and see what happens here. So if we put together the full expression for I like we did previously, okay, we know once again we can say that that was Ki times A minus Kp times I. And the way that we apply the steady state approximation to these equations is by setting this equal to 0. And so now what we can do is rearrange this algebraically, and we can say simply, okay, I is just going to be Ki divided by Kp times A. Okay, simple as that. And we also note here that technically speaking, these are the results I as a function, or I at any time t, and so that would be A at any time t. Okay. Well, we also remember that A had a straightforward solution, right? Because A only appears in one reaction, and so that straightforward solution for A, right, the unimolecular decomposition is just simply A at any time t equals A0 e to the negative KIT. So I know I wrote this next to this reaction, but this is true for this slow step, okay? So now I want to substitute that and see what happens, okay? So now, let's see here. I can say that I at any time is going to be Ki divided by Kp times A initial e to the negative KIT. So I can get a fairly straightforward expression for I. But more importantly, I can get a nice straightforward expression for P. Okay, so we recall that the rate law for P, you know, that we determined back here, right? It'll go the same way. dP by dt is just going to equal Kp, positive Kp, times I. And once again, we're trying to really figure out how much product we're making, but it's dependent on the concentration of our intermediate, which is not straightforward. However, what you can see here, what we can do, right, is substitute this new expression in, okay? And so that's going to go as the following. dP by dt equals Kp, now times all of this, which is Ki over Kp, A initial e to the negative KIT. Okay, and so you can see the Kp and the Kp are going to cancel. And so I'm going to do a little bit of algebraic rearranging. I'm going to say now dP equals Ki times A initial e to the negative KIT times dt. And we still need to divide and conquer. So we divided. So now let's conquer. And we do that by integrating from P initial to P at any time t. And I recognize that Ki times A initial is a constant. So I'll kick that out of the integral. And we'll just integrate this side from 0 to t. Okay. And so what we get here is this just becomes P at time t. So I know that it should be P at time t minus P0, but we know that P0 is equal to 0. So it just becomes PT, okay, equals. And so now we've got a little bit of algebra to do. So this is going to be Ki times A initial. And so then I'll just write the results of our integration. So we know we've got to integrate that from 0 to t. And the result, and that integral is going to be negative e to the negative KIT divided by KI. Okay. So now we know that when we substitute in t, it's just going to be e to the negative KIT. And when I substitute in 0, that's going to become 1. So I'm going to do a couple of algebraic steps here and write our final expression, which goes as the following. Okay. So then we know that P at any time. And so again, I'm just going to do all of the algebra here. I did it already. So pause the video and work through the algebra if you have to. But this is what you'll get. That P at any time equals the A initial concentration times 1 minus e to the negative. That says KIT. Let me make that a little bit less thick. Okay, so that's e to the negative KIT. And of course, our solution for A at any time is still valid. So that's still A. T equals A0 e to the negative KIT. And so now when we look at these final results, these are much more straightforward than what we got with these final results, right? This was my I at time t, and this was my P at time t. And you can see both of them, right? They're very similar in their functional form. And if we were to go through this, then we could actually arrive back to these situations by playing this game, saying, you know, what if we call Kp much greater than Ki, then Kp plus Ki is just functionally equal to Kp, and so on, right? If we kept going on and doing that, we would arrive at these expressions. And we also note here that these are nice, simple first-order expressions. So when we see a first-order production, it's always going to be 1 minus e to the minus kt. And when we see a first-order decay, it's always going to be e to the negative KIT. Okay? So beautiful. So that is that wraps it up for our Intro to Kinetics section. All right, folks. Hasta luego.